Hello, my name is Roberto Bagnara, and I am presenting joint work with Abramo Bagnara and Federico Serafini of BUGSENG. The presentation is about C-Rusted, which is a use of the C language for the development of safe, secure, and energy-efficient programs, in particular for those that have safety-related and security-related requirements. It's true there are many other programming languages, but you can find something, and typically something very critical, like operating systems and other middleware in every system that is written. And the reason why C is still so popular after half a century is that there are very strong economic reasons beyond the adoption of the language. So first of all, there is a wide variety of compilers that can generate very efficient code for almost any architecture. And compilers is just one of the ingredients of an enormous ecosystem that is available for C. So we have operating systems, hypervisor, testing and debugging facilities, network stacks, all sorts of tools that you can dream of are available for C. Of course, C has its own problems. In particular, it has problems related to safety and security issues. So in this slide, you can see that the number of vulnerabilities recorded by CERT is increasing steadily. And actually, the increase rate is growing. Half of these vulnerabilities are basically due to programming mistakes performed in C code. There are mitigations, of course. For example, MISRA compliance is one of the ways that industry has found to solve many of these language issues, but not all of them. In fact, we are at a turning point. So the industry and the regulators are so concerned about the safety and security issues of C code that a passage to Rust is actually being discussed in several circles, including circles you wouldn't expect, or at least you wouldn't have expected until a few years ago. So people is discussing to rewrite part of the Linux kernel, or maybe even the entire kernel in Rust. Well, of course, we cannot rewrite everything in Rust. So doing this will have an enormous cost. The question is, what if there was a safer and cheaper way? And in fact, there is. And our proposal in this respect is called C-Rusted. So the basic idea is that the borrow checker and all the other Rust machinery can be implemented also for standard C, for ISO C, preserving the entire C ecosystem, all the tools, and preserving all the huge investments that all industries have made on C. So let me try to show you how this works by means of example. Here we have a piece of C code, which a compiler like GCC will happily digest without giving a warning, even if you enable basically all warnings. In contrast, if you process this small source file with a C-Rusted analyzer, it will give you several warnings. Let's see some of them. So first of all, the POSIX open function, which is used to open a file, in this case for reading, returns an int. And this integer might be -1 in case open fails, maybe because the file is not there or for any other reason. Or it can be a file descriptor, meaning a small integer that is basically a handle to the file in some operating system structure. Well, even though a file descriptor is implemented as an int, it's not an int, meaning that, as it is done here in line 6, if you try to increment the file descriptor, you're actually invalidating it. At the implementation level, it's just incrementing an integer variable, which is perfectly fine, but for file descriptor, it doesn't make any sense. And this is why the call to read in line 7 is flagged, because FD might be -1 in case the open failed, but even if it didn't fail, the FD has been invalidated by the incrementation that was done in line 6. And the call to read has also another problem, because if malloc failed, then buff will be a null pointer, and calling read with a null pointer as the second argument gives undefined behavior. And so in line 8, we have two reasons why the C-rusted analyzer complains. We have that buff can be null, so we may be trying the referencing the null pointer, which is undefined behavior. But even if buff is not null, bytes may be -1 because the read operation failed. In this case, we have a buffer on the flow. The line 9, where we have a call to process passing buff, is also flagged, but the reason is different this time. It's not because buff may be null, but it's because there is no indication whether the process function will or will not deallocate the memory block pointed to by buff. And in C-rusted, this must always be clear. Who will deallocate memory? The return 0 is flagged for two reasons. Because maybe we are leaking memory because process possibly didn't deallocate buff and who is not deallocating it the same way. But we certainly are leaking a file descriptor in case the open function was successful. You see that we never called closed on such a file descriptor. Here we have a much saner version of the program that gives no warning by the C-rusted analyzer. The reason is that resources are properly managed here. So, for example, the fact that open might fail is correctly dealt with this test, where if fd is -1, then we simply return. The possibility of malloc to fail due to an out-of-memory condition is correctly handled, and in which case the file descriptor will be correctly closed. So if the read function fails, again, this possibility is detected here, in which case both the buffer and the file descriptor are properly disposed. And process of buff this time is not flagged because you see there is an annotation here. Process, yes, takes a char pointer, but a char pointer that is special. The call to process in line 17 is not flagged because process, yes, it takes a char pointer to keep allocated memory. This is the meaning of the H, and it takes ownership of its argument. And this is the meaning of a own, means process will take ownership, which means that it will either pass ownership to someone else who will eventually take care of deallocating the buffer, or it will deallocate the buffer by itself. So in any case, we don't have a leak memory leak condition on buff. And similarly, we don't have a file descriptor leak on close on fd because we always call the close function if we reach the end of function loop. So how is it that all this is achieved with just one small word here, own, just this small annotation on the process function? Actually, the reason is that the C-rusted analyzer treats standard libraries as if they were pre-annotated. It is as if the open standard function was declared in this way. Let me start from the beginning. So an FDT, a file descriptor type, is represented as an int, but it is a nominal type, meaning that it is represented as an int, but it's not an int. Okay, so the usual operation on int data cannot be performed on a file descriptor, and moreover, we annotate the file descriptor to specify that the value is always non-negative. And fd own t is like a file descriptor, but it has ownership of the file descriptions that is referred to by the file descriptor. And an fd own t also has the possibility of being -1. Why? Because as we said, open may return -1 in case of error. So this is why the C-rusted analyzer sees open as if it was declared in one of these three different ways, which are discriminated by the second argument that specifies whether we are opening for reading, in which case we obtain an fd own t with the read property, or with the write property, or with both of them. And similarly, the read, write, and close functions are seen by the serrated analyzer as if they were declared like this. First of all, we have a shareable reference to a file description, and this is fd_t. The read function takes an fd_t, but it requires not just any file descriptor, but a file descriptor with the read property, for otherwise we cannot read from it. And similarly, the write function requires a file descriptor with the write property. And the close function will take ownership of the file descriptor that is passed as an argument. So this reflects the fact that close will take care of disposing the file descriptor. We see here in the example that there are serrated annotations also for annotating the return value. So here we see that read and write will always return a value that is greater than or equal to -1, whereas close will either return -1 in case of error, or it will return 0 in case of success. Nominal typing is a powerful concept. We have seen it in action on standard library functions and data types, but it is placed by serrated in the hands of programmers. Here, for example, the programmer is declaring nominal types for Celsius degrees are represented in double, but they are not double. They are a nominal type, so the usual functions, the usual operation on double are not allowed unless they are explicitly enabled. And so similar, we have a Kelvin T type, which is a nominal type represented in double, and we have a type for delta Celsius and delta Kelvin. Then we have a declaration saying that if we do Celsius minus Celsius, we obtain a delta Celsius. If we do Kelvin minus Kelvin, we obtain a delta Kelvin, and we can even divide Kelvin degrees. If we do Kelvin divided by Kelvin, we obtain a double. Notice that we are not saying that we can divide Celsius degrees, and in fact, from the physical points of view, this doesn't make any sense. And since division of between Celsius degrees was not explicitly enabled, this division is flagged by the serrated analyzer. Here is another example where we use this concept. We have seen already owning references and shared references. Let's now see also exclusive references. Here we have a declaration for an element of a singly linked list where the payload is simply represented by an int, and the next pointer, it's not just any pointer, it's annotated with opt_own, meaning next is a pointer to list T, which may be a null, and this is the meaning of the opt part. And if it is not null, it's a pointer to an heap allocated memory of which it has ownership. Now, let's consider this function. List print will only read from a list, and so it can do its job with a shared reference, which is annotated in this way in serrated. In contrast, the list pushback function will have to modify the list, so it requires an exclusive reference to the list. And of course, an exclusive reference is incompatible with the existence of any other exclusive or shared references, because if we have more than one exclusive reference and we have more than one writer to a data structure, of course, we risk the race conditions and bad things. The list-free function will take ownership, so you can pass the null pointer to list-free, and it is represented by this opt particle here, and otherwise, it will take ownership for some heap allocated memory, and it will take care of proper deallocation. Chain of resource management, this is placed, as I said, by serrated in the hands of programmer. For example, here we have a channel data type, which requires finalization, and this is expressed by this eFINI annotation. It has a constructor, which is expressed by this init. It has a send function for sending messages across the channel, and it has a finalization function, the channel destructor. Here we see an example function that declares a channel. At line 11, problem is that the channel has not been initialized, and so this is why this is flagged by the serrated analyzer. So in order to actually send something across a channel, we need first to construct it. So here in line 12, we initialize the channel by calling channel constructor. At this time, we can send a message across channel C, But you see that the return in line 13 is flagged, and the reason is that if we return here, we failed to properly deallocate the channel. So the channel destructor will not be invoked if we return in line 13. And this is, of course, flagged because this is not in the safe evolution of the resource. And the programmer can also write more complex properties. So let me try to illustrate this mixer example. A mixer is somehow safety critical because if the door is open and the blades are running, then people may get hurt. We use crafted to annotate the mixer open function that will open the door of a mixer, and as a requirement, the in annotation, the requirement is that you can only call this function if you are passing a mixer where the blades are off. On output, on function return of mixer open, the door will be opened. When you call mixer closed, it returns, then the door will be closed. If you want to turn on a mixer, then you have the requirement that you can do this only on a mixer whose door is closed, and on output you will obtain a mixer where the blade is on. And when you call mixer off, the mixer off function, then as a result, on return, you will have that the blades are off. Here we have a function foo that requires a mixer with blades off, and on output, it may leave the door open or closed. This is the meaning of the question mark. So here we have a first violation, meaning that we are calling mixer on a mixer of which we don't know that the door is closed, but this is a requirement. Okay. So in order to call mixer on, we must be sure that the door is closed. So this is illegal. Whereas if we first close the door, then we can turn on the mixer, and this will give no warning by the serrated analyzer. What's the problem of this return, which is flagged by the analyzer? Is that the blade is still on, whereas function foo has been declared to have blade off in input, and whenever the output condition doesn't specify anything different, means in serrated that the input condition must be pursued. So the blades were off in input, and since nothing to the contrary is written in the output specification, the blades must remain off. So all this is done by using static analysis extensively. Of course, the static analysis is rigorously intra-procedural, so the semantics of function is captured, as I have shown, by explicit and implicit annotation, and this ensures scalability, incrementality, and modularity of the analysis. The static analysis techniques are not new. We are simply reusing technology that is available since a long time. Here I'm showing one of the domains used by the serrated analyzer in order to reason on the evolution of all resources. Here we see that a resource starts in the uninitialized state, and when it is properly initialized, it becomes readable. You see here that there are some edges that are depicted in solid lines, and this means that these transitions are possible in any resource, whereas there are transitions that are rendered with dashed lines, and so these may or may not be enabled. For example, attempting writing to a resource may not be possible if the resource is read-only, for example. And another interesting thing is the support serrated as for security. You can see that you can certainly release an uninitialized resource. You can release a finalized resource, but you cannot in general release a resource in any other state. And the reason is that when security is of concern, for example, a piece of allocated memory may contain confidential information. So if you simply call free, you are possibly giving ways to an attacker to obtain this confidential information. So in this kind of resources, all the release dashed arrow will be inhibited, and only the finalized to release transition will be enabled. In this table, we compare C rusted both with C and Rust, and it can be seen that C rusted joins the good things of C with the good things of Rust. First of all, rusted is ISO C, so it is standardized. There exist certifiable compilers for C rusted exactly as they are available to C. It's portable exactly as C, and there is a large availability of tools and developers. Our coding standard for safety and security, MISRA C, for example, is applicable to C rusted exactly as it is applicable to C. And in fact, there is also a quite nice synergy between MISRA C and C rusted. Of course, you can reuse C legacy code because C rusted is C again, and exactly for the case of Rust, you can have strong guarantees both on memory resources and on user-defined resources for annotated programs. There is complete compatibility with an annotated code because an annotated C rusted code is C code. And incremental adoption is clearly an important feature. There is no requirement that you annotate all of your C code. You can start with the most critical functionality and then proceed in an incremental fashion. You don't have to retrain C programmers for an annotated code because C rusted unannotated code is C code. You can also retrain C programmers for annotated code in a simpler way than for Rust, meaning that we strongly believe that a good C programmer can be trained to use C rusted in a week of time. And training a C programmer for using Rust in a good way is much more expensive. Here is our roadmap for C rusted. We are currently working on a book with a full language definition, and this will be published later this year. We have an implementation of the C rusted analyzer within the Eclair software verification platform, which is currently under alpha testing. And when this is done, we will launch an extensive campaign of beta testing, and we will release the first instance of the C rusted analyzer with the next version of Eclair, which will be certified by TÜV according to the most important functional safety standards up to the highest criticality level. Thank you for your attention. Bye-bye.